So the substitution rule, kind of nice for the AB exam. If the function you're trying to take the integral of doesn't look like, isn't, boy, this is just a straight integral of sine, integral of cosine, things like that. There's only one other option, and that's using this thing called substitution, which is really, basically, it undoes chain rule. It's the inverse to chain rule. So if we had a function like 2x times the square root of 1 plus x squared, up until this point, we'd be stuck. So what we're going to do is we're going to make a substitution. And we're going to let u equal the inside part of this square root, 1 plus x squared. And then we're going to take the differential, which again, that's just the derivative, except instead of du over dx, we get du equals, and then the derivative of 1 plus x squared is 2x dx. And so what we'll do is we'll take the 1 plus x squared and replace it with u. It was so much easier when I didn't have to worry about this at home. Just kidding, just kidding. I'm glad to be here. And we'll put the u in there. And then the 2x dx gets replaced with du. And then we can deal with that. So what we're going to end up with is the integral of u to the 1/2 du. Something that we can handle pretty easily. So we end up with this u to the 1/2 du. And we can take the integral of that. We add 1 to the power to get u to the 3/2. We then divide by that new power or multiply by its reciprocal. So dividing by 3/2 is the same as multiplying by 2/3. Because we don't have limits on our integration, it's an indefinite integral, we have to add a constant to the end. So we put that plus c. And then the last step, great that we have it in terms of u, but our original integral was in terms of x. So we want to back substitute or reverse substitute or however you want to think about that. to get 2/3 times the quantity 1 plus x squared to the 3/2 plus c. So a statement of the substitution rule: if u is equal to some function g of x, and g of x is a differentiable function over some interval I, and if the function f is continuous on that same interval I, then the excuse me, the integral of the composition f of g of x times g prime of x dx is equal to the integral of f of u du. Again, making that substitution, u gets plugged in for g of x. There are generally 4 types of problems, maybe 5, where substitution is helpful. Trig functions, often you can take like sine of a function. So trig functions oftentimes. Root functions could be a power function, x squared plus 2, the quantity to the 5th or whatever. Logarithms, exponential functions, and then the one that is pretty familiar, probably most often used, is rational functions, where we have a fraction with x in the denominator. And if you have a rational function, 99 times out of 100, the denominator is what's going to be your u. All right, so let's try this one. 2x plus 1 to the 1/2 dx. So I know right away I'm going to need substitution because I have a composite function. And so if it's a composite function, my u is going to be the inner part of that composite function. So in this case, the inner part of the composite function is 2x plus 1. Yeah. Excellent. Taking the derivative or the differential du is equal to 2 dx. And we have a problem. I mean, I have the dx, but I don't have that 2. As long as it's a constant value, I can deal with that. What I'm going to do is solve that expression du equals 2 dx. I'm just going to solve it for dx. I'll divide both sides by 2 or multiply by 1/2. Once I do that, then instead of 2x plus 1, I'm going to substitute in u. And for the dx, I'm going to substitute 1/2 du. And I'll do it this way, but I will. Most of the time, if I have a substitution like this, I'm going to take that 1/2 and put it in front of the integral, because we do have a property of integrals that says I can do that. And now if I integrate, there we go. Bless you. Add 1 to the power. Divide by that power or multiply by its reciprocal. And it's an indefinite integral, so add a constant to the end. I would reduce it. Again, on the AP exam, you don't have to. I just think it looks better. And the last step, u was equal to 2x plus 1. So I have my integral then in terms of x. Make sense? All right. Guess I should have warned you, be ready for your mind to be blown. Here we go. Integral of tangent x dx. In this case, I don't really have a composite function. I mean, technically I could say tangent is a composite function, but if all I do is change this from x to u, I haven't helped myself any. I'm still taking the tangent. So, skip to the next problem. No, we're going to rewrite tangent. Tangent is sine of x over cosine of x. And now I have a rational function. And so I'm going to let my u equal the denominator. Then taking the derivative, du is equal to negative sine x dx. Again, I have sine x dx. I don't have that negative. So I just solve. So I get sine x dx on one side. I'm going to have that negative then on the other with the du. So my substitution I'll get a negative. The sin x dx gets replaced with the negative and the du. And then I get u in the denominator. When I integrate, I'm going to get a negative. What is the integral of du over u, or 1 over u du? Natural log, right? When I take the derivative of a logarithm, I get 1 over whatever I'm taking the logarithm of. Key when you're integrating, when you take an integral and get ln, you're going to put absolute values in. Because ln is only defined for positive values. Substitute cosine in for u. And so one possible answer would be negative ln of the cosine of x plus a constant. I say one of the answers because with logarithms and trig functions, there are several ways that you could rewrite this. For instance, I could bring the negative inside as a power. And cosine to the negative first is 1 over cosine, and that's secant. And so that's correct and not a problem on a open-ended free response type question. You might see it written this way if the question was multiple choice. So just be aware of that. The multiple choice, they can use those great identity things and rewrite functions that way. All right, don't write that down. Let me do this. Because we got a little bit more to do. I guess you could write that down. It wouldn't have been a big deal. All right. I'm going to take that back. Go ahead and write that down. That'll be part of your assignment. One through 6, they are going to give you your function, take the integral, but then they're going to tell you what to use for u. So they're actually going to do like 90% of the work for you. It's kind of nice, good way to ease into it. And then 7 through 19, you'll have to do the whole thing. All right. The other part that we need to talk about is what happens when we have a definite integral. So if we have a definite integral, there are actually two options. One that I really like and use all the time, and one that works. It tends to be, I think, a little more work, but I'll show it to you both ways. So again, we have our derivative of g is continuous on the interval from a to b, and the function f is continuous on the range of u equals g of x. Then the integral from a to b of f of g of x times g prime of x dx is the integral from g of a to g of b times f of u du. I have to be careful when I teach this lesson. It's f of u, not fu. F of u. All right. So we actually did this integral on the previous first part of the notes, but now we're going to evaluate it from 0 to 4. So we have the integral from 0 to 4 of 2x plus 1 to the 1/2 power. So we can still let our u, wow, equal 2x plus 1. Our du would be 2 times dx. And we don't have that 2, so we would have to divide and get 1/2 times du equals dx. So to this point, and I'm going to not write the limits for just a second. These limits of 0 and 4 are limits with respect to x. So we have two choices. One choice would be to write them in terms of u, which is the option I like. The other is to leave them as 0 and 4, take the integral, back substitute, and then plug in 0 and 4 in for x, which you can do, and it works. As I said, the other one option would be take 0 and plug it in for x right here. So we get 2 times 0 plus 1. Take 4 and plug it in for x. And so in terms of u, this would be 1/2 times the integral from 1 to 9 of u to the 1/2 du. Again, the other option would be and I use the x equals to remind myself I've got to do that back substitution before I evaluate. And that little thing there is a 2. There we go. All right. So on the left-hand side here, I get 1/2 u to the 3/2, and then I do have to multiply that by 2/3. And I'm evaluating from 1 to 9. So I get 1/3, 9 to the 3/2, minus 1 to the 3/2. Nine to the 3/2, well, that's the square root of 9 cubed. Or you could say, let's cube 9 and then take the square root. I prefer to do the square root first. Again, usually a little bit easier to work with. 1 to the 3/2. Square root of 1 is, that one you could cube first. It probably wouldn't affect your answer a whole lot. So if you change your limits, again, it's kind of a quick shot right to the answer. If you decided not to, it works. There's not a problem with it. You would still get this 1/2 times 2/3 u to the 3/2. It'll be 1/3 2x plus 1 to the 3/2. And now you'd have from 0 to 4. So basically you would plug in 4, plug in 0, and subtract. Whereas on this side, you plugged in 0 and 4 already, right? So it's just a question of when you evaluate plugging in 0 and 4 into your function. So oops, 0. I mean, I think we can see 8 plus 1, 9, 9 to the 3/2. 2 times 0 plus 1 is 1 to the 3/2. And so it doesn't matter when you do that substitution. To me, I like to do it early And then it's just a little less work later on. But again, you can be successful either way. Last bit of information from this section deals with symmetry of functions and what that does to the integral. Generally, when we talk about symmetric functions, we talk about odd functions and even functions. If we have a function f, it's continuous from negative a to a, and f is even. If you have the integral from negative a to positive a of f of x, that's the same as 2 times the integral from 0 to a of f of x dx. So a couple of things with symmetric functions. You have to go from the opposite of a value to that value, okay? And then you have to know you have an even function. So in terms of, and we talk about one way to think about an integral is area under a curve. So if I have this even function, what we're saying is the area on the right side and the area on the left side are the same. So rather than going from negative a to a, let's just go from 0 to a and double it. Even functions pop up maybe a little more frequently than the next one we're going to talk about, the odd function. So it's sometimes helpful and useful because, especially if f is a polynomial, so you have an x in every term, plugging 0 in really makes quick work of things. If you don't recognize this, what's going to happen is you're going to get a number minus the opposite of it. So it still works out if you don't recognize the symmetry part. This one, however, is much more fun. If the function is odd, then the integral from negative a to a is 0. It's okay, my drawing wasn't great, but basically what we're saying is there's as much area below the axis as there is above the axis. It cancels it out, gives you 0. So if you ever have an integral and you're just going, man, I have no idea what that integral would be, look at the limits. If they're opposites, check to see if it's an odd function. Then you can just write 0 and go on. If it's even, then you're still stuck. You got to find out how to take the integral. So 41 to 50, I believe, are definite integrals, dealing with those values now, and 67 and 68 deal with symmetric functions. All right, you've got about an hour, not quite, to work.